Good morning, my YouTube viewers. It's Crystal here. In this particular video, what we're going to be discussing is regression. And a lot of people may not realize this, but especially if they have studied machine learning before they studied statistics. But although regression is a part of machine learning, and it's a very big part of machine learning, regression was actually a part of statistics before it was ever part of machine learning. And the reason why is because statistics is a much older discipline than machine learning is. So regression started out in statistics, and then when machine learning became a science, it moved over to machine learning, but it's still a part of statistics, and it was originally a part of statistics. So that's what we're going to be discussing in this video is regression. And in this video in particular, we're going to be studying simple linear regression. So regression analysis is a predictive modeling technique that examines the relationship between a dependent variable, the response, and one or more independent variables, the predictors. Unlike correlation, regression provides an explicit equation to describe this relationship, enabling predictions and interpretations. So that is the overall definition of what regression is. But what we're going to be discussing in this video is simple linear regression. And simple linear regression is where you have one predictor, which is one independent variable, and one response, which is one dependent variable. So generally X is going to be your independent variable and Y is going to be your dependent variable. And that's called simple linear regression. But before we get into simple linear regression, then what we're going to be talking about is least squares. Least squares is another component in the science of regression. So basically, least squares is the core mathematical idea behind linear regression. It is the rule the model uses to find the best fitting line through the data. Least squares is the method that chooses the regression line by minimizing the total squared vertical distances between the observed data points and the line. The vertical distances are the residuals, and the squares find the slope and the intercept that minimize. In essence, least squares finds the line with the least total squared error. And in order to demonstrate the least squares, we've got a small program written in R that will show you what least squares is. So if you can see a visual representation of least squares, you'll have a better understanding of what it is. So the first thing we're going to do is we're going to set our seed. And the reason why you set your seed is because every time you run the program, it will initialize the variables to the same value. So you type set.seed brackets 1, 2, 3, and you can put any number you want in there. It doesn't matter. And now we're going to simulate our data. So X becomes our norm. That's a randomly sampled normal distribution. Brackets 20, that's 20 samples, a mean of 10, and a standard deviation of 3. So that's your independent variable X. And then you've got Y becomes 5 plus 2 times X plus our norm. That's your randomly sampled normal distribution. Brackets 20 for 20 samples and a standard deviation of 4. So that is your dependent variable, which is Y. And now what we're going to do is we're going to fit the linear model. So model becomes LM, meaning and LM stands for linear model, and then Y, squiggly X. So Y is your dependent variable and X is your independent variable. And then we're going to predict the values. So Y hat becomes fitted brackets model. So that you're going to fit that. And we're going to plot our regression line. So plot brackets X, comma, Y, comma, PCH, that's the size of the dot, is 19. Color is still blue. Main, that's your title, is least squares demonstration. X lab is your label on your x-axis, is X. And Y lab is your label on your y-axis, is Y. So we're going to add a regression line, AB line, brackets, model, color is red, line width is 2. And then we're going to add residual segments, which are vertical lines. So segments, brackets, X, comma, Y, comma, X, comma, Y hat, comma, color equals dark gray, comma, line width equals 1.5. We're going to add squared residuals as shaded rectangles for, so we're going to have a for loop, for I in 1 to length of X. And so I think X has 20 elements in it, so I think it's 20. Where were we? Rect brackets xi, so that's going to be the number of the element, minus 0.1, comma, min brackets yi, comma, y hat I, and then comma, and then you have xi, which is the number of the element in I, and I think that we've already said the length of X is 20 because it's 20 samples, plus 0.1, comma, max yi, comma, y hat I. And color equals, so you're going to have a vector of colors. It's RGB, brackets 1, 0, 0, 0.2, and you're not going to have a border. Now we're going to add your R squared equation. So BO becomes coefficient of model position 1. B1 becomes coefficient of model position 2. And then R2, that's your R squared, becomes summary model $R squared. And then we're going to put some text in there. And we're going to say text brackets min X, comma, max Y. So that's the minimum value of X and the maximum value of Y, comma, we're going to put labels equals paste 0. That's kind of like a print command, brackets, Y equals round BO, comma, 2. So you're going to round it, plus round B1, comma, 2. So you're going to round it, and then of X, and next line. And then R squared equals round R squared R2, comma, 3. So it's rounded to 3 points. Position equals 4. Color equals red. So we run it. And this is your least squares demonstration. This is the plot that we picked out. So the red line is your regression line. That is the formula for linear regression. The gray dots are the actual points of X, because I believe you should have 20 there, because when we simulated our data, we said that it was going to be a sample of 20. So you should have 20 points in there. And then the lines from the point to the line, that is your least squared. That's telling you how far away the actual point is from your prediction. And so basically what you want is you want those tiny little red-gray lines to be as close to the regression line as possible. And so the closer they are to the regression line is going to be the better fit and the higher the accuracy. If the points are far away from the regression line, then that means it's not a very good fit and it's not going to have high accuracy. So that's just a visual demonstration of least squares, so you can see how least squares works and understand it better when you're doing your linear regression. So now what we're going to do is we're going to do a program using simple linear regression. And simple linear regression is you have one independent variable x and one dependent variable y. So the first thing that you're going to do is you're going to set your seed. And the reason why you set your seed is because every time you run the program, the variables will be initialized to the same value. So you set.seed brackets 1, 2, 3. You can put any number you want in there. It doesn't matter. Then we're going to simulate our data. So advertising becomes our norm. That's randomly sampled normal distribution. Brackets 50. That means it's 50 samples. Mean of 20 and a standard deviation of 5. And sales becomes 3.5 times advertising plus our norm, that's a randomly sampled normal distribution, brackets 50, which is 50 samples, mean of 0, and a standard deviation of 8. So you can see that the mean in the sales is much less than the mean in the advertising, but the standard deviation in the sales is more than the standard deviation in the advertising. And so now we're going to generate our data into a data frame. So data becomes data.frame, brackets, advertising, and sales. So we're going to create a data frame that has advertising and sales in it. And what I could have done is I could have typed data down there. Okay. We'll run it again. So we run it again. We're going to see the data. So this is the data frame that has been created. And so the data frame that has been created, you can see all the values in the data frame. So the first column is advertising and the second column is sales. And you actually have 50 actual rows. But if you don't want to see all 50 rows, which I don't want to see it, then what you could do is you can say, I think you're going to do it this way. Head to data. I think that's what we're going to do. And then so what that does is instead of seeing all 50 rows, which is a lot to look at, then what you're going to do is you're going to see the first 6 rows. So now that you've seen the actual data frame, we're going to fit the simple linear regression. So your model becomes LM, that's for linear model, brackets, sales, a squiggly, advertising, comma, data equals data. So that's your linear regression model. And then we're going to type, you're going to see a summary of the model. So this is a summary of the model. So this is, you're going to have your, what the linear regression model is. You're going to have your residuals, which are the minimum value, the first quartile, the median, the third quartile, and the maximum value. You have your coefficients, which is your estimated standard deviation, your error, your t-value, telling you that they did this on a t-distribution, and your p-value. So your p-value is 0.64. And then you're going to have some more cones. So your residual standard error is 7.314 on 48 degrees of freedom. And your multiple R squared is 0.8291. Your adjusted R squared is 0.8255. Your F statistics is 2.32.8 on 1 and 48 degrees of freedom. And your p-value is a really low number. It is 2.2 to the negative, it says 2.2e to the negative 16. So that's a little bit odd. And the reason why, because on the intercept, the p-value is 0.64, but on advertising, the p-value is a very low level. So we've printed out a summary of the model, and now what we're going to do is we're going to plot the regression line. So, and the equation and R2. So plot brackets, advertising, comma, sales, PCH, that's the size of the dot, is 19. Color equals still blue. Main equals simple linear regression. Sales versus advertising, and that's your title. XLab is your label. On your x-axis is advertising spend. YLab is your label on your y-axis, which is sale. So on the x-axis, X, you've got your advertising spend, and Y is your sales. So X is your independent variable, and Y is your dependent variable. And then we're going to add the regression line. So AB line, brackets, model, color equals red, line width equals 2. And then we're going to extract the coefficients. So BO, or B0, becomes coef, brackets, model 1. B1 becomes coef, brackets, model 2. R2 becomes summary, model $sign R squared. So we're going to add an equation to R squared to plot. So we're going to put some text in there. So text, brackets, min, brackets, advertising, comma, that's your minimum, and your max is your sales. Min advertising, min the value of advertising, and max the value of sales. Labels equals paste 0. That's a type of print command. So Y equals rounded BO to 2 points plus rounded B1 to 2 points. And then next line, R squared equals R squared rounded to 3 points. Position equals 4. Color equals red. So we print it off. We run this program. And this is what we've got. A simple linear regression line with sales on your y-axis and advertising on your spin. And so you can see you've got your red regression line is the red line, and then you've got the blue dots, which are the points of the data that we have created, and they don't have the little lines going from the blue dots to the regression line. But ideally what you want is the blue dots to be as close to the regression line as possible. So if the blue dots are as close to the regression line as possible, then that means this is a good model, it's a good fit, and a high accuracy. And then if the blue dots are not close to the regression line, it means it's not a good fit and it's not high accuracy. So now what we're going to do is we're going to fit, interpret, and plot a simple linear regression model. And so we're going to set the seed. So you set your seed so every time you run the program, the variables initialize to the same values. So you say set.seed brackets 1, 2, 3, can be any number in there. And then we're going to simulate the data. So ours becomes R norm. That's a randomly sampled normal distribution. Brackets 50, comma, mean is a 5 and a standard deviation of 1.5. And then your score becomes 12 plus 8 times ours plus R norm. That's a randomly sampled normal distribution. Brackets 50 and a standard deviation of 5. So that's your scores. And then your data, we're going to create a data frame. And the data becomes data.frame brackets hours and score. So if you want to see the data, you can say head. And what that's going to do is that's going to, I messed that up, didn't I? What that is going to do, that's going to allow you to see the first 6 rows of the data frame. So here we've got the first 6 rows. So your hours is your X variable, is your independent variable, and your score is your Y variable, and it is the dependent variable. And then if you want to see the last 6, rows of this data frame, then you just type tail data, and that will give you the last 6 rows of the data frame. So now we're going to fit a simple linear regression. So model becomes LM. LM means linear model, brackets score, squiggly hours, comma, data equals data. And then you're going to summarize the model. So you've got summary model. So we come down here and we've got a summary of the model. This is your summary. So it says call LM, that's linear model, formula equals score, squiggly hours, comma, data equals data. Then you've got your residuals of your minimum, your first quartile, your median, your third quartile, and your max. Then you've got your coefficients with an estimate, standard error, your t-value, which means you're using this on a t-distribution, and your p-value. So on your intercept, your p-value is a really low value, and on your hours, your p-value is a really low hour value as well. So you've got your significant codes, you've got your residual standard error of 4.571 on 48 degrees of freedom. You got your multiple R squared is 0.8541. Your adjusted R squared of 0.8511. You've got your F statistic, which is 281.1 on 1 and 48 degrees of freedom. And you've got your p-value is 2.2 to negative 16. So you see you've got a really low p-value. So we're going to interpret this model. So the intercept of B0 is the expected exam scores when hours equals 0. The slope B1 is how much exam score increases for each additional hour studied. R2, that's your R squared, is the proportion of variation in exam scores explained by hours studied. Your p-value for your slope tests whether hours studied is a significant predictor. I'm sorry, my thinking is much better than my typing. Now we're going to plot the regression line, equation, and R squared. So plot brackets, hours, comma, score, comma, PCH, that's the size of the dot, is 19. Color is still blue. Main is the title, is simple linear regression, exam score versus hours studied. X lab, that's your label on your x-axis, is hours studied, and that's also your independent variable. Y lab is the label on the y-axis, is the exam score, and that's your dependent variable. So we're going to add a regression line. So you've got AB line, brackets, model, color equals red, line length equals 2. We're going to extract the coefficients. So B0 becomes coef, brackets, model 1. This is the first element in the model. B1 becomes coef, brackets, model 2. That's the second element in model. R2, that's your R squared, becomes summary, model, $R dot squared. And then we're going to add an equation plus R squared to the plot. And then you have text is going to be the min hours, comma, max score, comma, labels equals paste. Score is going to be B0 rounded to 2 and plus B1 rounded to 2 hours. Next line, R squared equals round R squared to 3 points. Position equals 4. Color equals red. So we run that up, and this is the graph that we've got. Simple linear regression, exam score, hours versus, exam score versus hours studied. So your hours studied is your X variable or your independent variable. And your exam score is your Y variable or your dependent variable. And basically what this chart is telling you is that the more hours you study, the higher your exam score is going to be. That is what this chart is telling you. So now what we're going to do is we're going to predict a numeric outcome using simple linear regression. So we're going to set the seed. And so what happens when you set the seed is every time you run the program, the variables are going to be initialized to the same value. So we're going to type set.seed brackets 1, 2, 3. You can put any number you want in there. And then we're going to simulate our data. So ours becomes our norm. That's a randomly sampled normal distribution. Brackets 50, that's 50 samples with a mean of 5 and a standard deviation of 1.5. Score becomes data.frame. No, score becomes 15 plus 7 times hours plus our norm. That's a randomly sampled normal distribution of 50 samples and a standard deviation of 6. Data is your data frame, meaning which becomes data.frame, hours, and score. So what we're going to do is we're just so you can see the data frame. We're going to type head data, and that's going to show you the first 6. And if you want to see the last 6, then what you do is you type tail data. But we're just going to say head data here. So you can see the first 6 rows of the data frame. So you can say the first column is X, and that's your hours and your independent variable. The second column is score, and that is your Y value, and that is a dependent variable, and you can see the first 6 rows of that. If you want to see the tails, then you type tail brackets data. That will give you the last 6. So we're going to fit a simple linear regression. Model becomes LM, that means linear model. Bracket score, squiggly, and I think they call that a tilde. Hours, comma, data equals data, and then we're going to summarize the model. So this is a summary of the model. So you're going to call LM brackets formula equals score tilde hours comma data equals data. Then you've got your residuals of your min, your first quartile, your median, your third quartile, and your max. Then you've got your coefficients for your intercept and your hours being estimated, estimate standard error, t-value. That's telling you that it's using the t-distribution and a p-value. And then basically your p-value is a very low value. You've got your significant codes. Then you've got your residual standard error being 5.485 on 48 degrees of freedom. You've got your multiple r squared is 0.7548. You've got your adjusted r squared is 0.7497. You've got your F statistic of 147.8 on 1 and 48 degrees of freedom. You've got your p-value is 2.91 to the negative 16th. So that's really low. That's a really low value. So now we've summarized the model. So we're going to predict a new outcome. So a new student becomes data.frame and hours equals 6. So this student is studying 6 hours. And predict score becomes predict brackets model comma new student. And we're going to run it. And we're going to get the predicted score. So let's say they studied 6 hours, so they got 57.74 is their score. So just to show you how this works, we're going to change the hours to, let's say he studied 20 hours. I hope I didn't go over myself, but let's say that he studied 20 hours. So he'd score 153. So obviously I went too much because ideally the score is not going to be any higher than 100. But if he studied 20 hours, he had a score of 153. So let's say that he studies 10 hours. So let's go back and see what happens when he studies 10 hours. So he's got an 85 percentile or 85 points if he studies 10 hours. So now what we're going to do is after we've made our prediction, we're going to plot our regression line and prediction point. So plot brackets hours, comma score, comma PCH equals 19. That's the size of the point. Color equals still blue. Main, that's your title, is predicting exam score using simple regression. XLab is the title of the X label. It's hours studied. And Y lab is the label of the exam score, which is exam score. So we're going to add a regression line. So it's AB line, brackets model, comma, color equals red, line width equals 2. We're going to add the predicted point. So points, brackets 6, comma, predicted score. So let's move this to 10. Let's run this again. So we said because we had 10 hours, we changed it to 10 hours study. So I think that it should be 10 and not 6. Brackets predicted score. PCH equals 19. That's the size of the dot. Color equals dark green. CEX equals 1.5. The annotated predicted point equals text. It's going to be 10. So we're going to run that again. Brackets, predicted score, labels equals paste, brackets, predicted equals rounded predicted score to 1 decimal point, POS equals 4, and color equals dark green. So we're going to look at the chart that we've created, even though I have changed the text on it. So it's not even there because the exam score goes up to 7, and our exam score was 85. And then your hours studied only goes up to 8. So what we're going to do is we're going to come back here to the code again, and we're going to say hours studied equals 7. So we're going to run it again since I have changed the hours studied, see if it works. Yeah. So the actual chart itself, the hours studied doesn't go any higher than 8, and the exam score doesn't go any higher than 70. And then so with 7 hours studied, you get a score of 64, and that actually does show up on the chart. So that concludes this video because we've covered all of the topics that I want to cover on simple linear regression. So the next video that I make is going to be multiple linear regression. So I hope that you got something out of this video, and I hope that you decide to watch the next video, and I will be communicating with you soon.